Hi everyone, I'm Kaushik and I've teamed up with Anand to work on the task of modeling chromatin insulator loops using variants of transformer-based architectures that has been popular in the recent literature. We start our research from the work proposed in the Deep Milo paper published in 2020 by a group at Cornell. In this paper, they divide the insulator loop prediction task into three different subtasks. The first task is to predict anchor regions. We could think of this as a binary classification problem where we predict if an arbitrary sequence of 4,000 base pairs is an anchor region or not. In the second task, given a known anchor region, the model predicts if it's a right anchor or a left anchor. And the final task is to identify the chromatin loops where we're given the pairs of identified anchor regions from the two prior tasks. However, we limit the scope of this research only until the first task, as we had incomplete data from the authors for the two other tasks. We perform our experiments on 6 different architectures. The 3 on the left were proposed in the Deep Milo paper. However, we re-implemented their code in PyTorch and performed the experiments with the same hyperparameters. The 3 on the right are our proposed architectures for this research. The first architecture we experiment with is a vanilla bird with CNN layers stacked on top with similar intuitions as the Enformer architecture. For the next model, we use a pre-trained DNABERT and fine-tune it for the anchor prediction task. For our final model, we use the Enformer architecture and train a smaller version of the original architecture in the Enformer paper. Next, we look into the distribution of the negative samples among the data we use. There are 3 different variants of negative samples. 50% of the negative samples consists of CTCF motifs and chip-seq peaks. 30% are with CTCF motifs but no chip-seq peaks, and the remaining 20% are negative samples with no CTCF motifs or chip-seq peaks. Next, Anand is going to talk about our results and observations of the experiments.
Thanks, Kaushik. This table summarizes the area under the precision recall curve for all of our models across the test sets. The top 3 are Deep Milo, the bottom 3 are ours. Unfortunately, we weren't able to get our CNN-BERT combined model to converge, but we were able to fine-tune DNABERT and train a small Enformer from scratch. We can see from the results that both of our models outperform the baselines on the type 1 and type 2 test sets, but perform significantly worse on type 3, and the positive examples are the same across these 3 different test sets. What's unusual here is that the type 1 and type 2 negative examples are supposed to be very similar to true anchors, certainly more so than type 3, so it should be much more difficult to predict the type 1 and type 2 non-anchors than it is for the type 3 ones, and yet our models are performing better for those two. In order to try and understand this, we need to dig a little bit deeper. Here are the precision recall curves for many of our models. The chart at the top shows all of our models on the type 1 test set, and we can see the purple Enformer here outperforms all of the others. And the bottom 2 charts show the Enformer and DNABERT on all 3 test sets. The type 3 curve is green, and we can see that this is considerably worse than the other 2 test sets. There's 2 insights that we gained about this that might explain why. The first deals with capacity. The original DNABERT and Enformer models were quite large. However, in our case, we freeze many of the DNABERT layers, and our Enformer is smaller by design. So it's possible that both of our models aren't large enough to capture expressive representations of DNA sequences to be able to distinguish true anchors from arbitrary regions of DNA. The second insight deals with balance. Most of the training set's negative examples are type 1 and type 2. This imbalance was done intentionally by Deep Milo so that their CNN and LSTM models could better identify these regions since they're similar to true anchors, but it may be backfiring for transformers. Our models might be spending too long trying to distinguish the fine details between a true anchor and a very similar type 1 non-anchor, as opposed to the perhaps broader differences between an anchor and some arbitrary region of DNA. So we think that balancing these types, as well as increasing the size of our models, might improve performance beyond what we're seeing here. With that, I'd like to thank you for your attention. Remember, this is only anchor prediction and not orientation or loop prediction. So we would welcome any discussion about how to extend this work further into those tasks and potentially turn this into a publication. Thank you.